Hi there. I want to ask you a very simple question, and that is, when was the first time you learned about the solar system? Perhaps if you kind of reminisce and think back a little bit, those might be your elementary school days, right? Where you learned about the planets around the sun and maybe even some clever mnemonics to remember those planets. And I mean, because you learned it at school, it must be right, right? Perhaps if you're more enthusiastic about astronomy, which I'm guessing you are based off the fact that you clicked on this video, then you might have heard about the history of people like Isaac Newton, Galileo Galilei, Johannes Kepler, and you know that this was like a trajectory to how people came to know about the solar system. And it is this trajectory that I want to highlight as well, because this trajectory is extremely important and kind of showing that these ideas didn't fall from thin air, like they came from somewhere and they came from a long progress of somewhere. And also, it shows a deeper, you could say, elegant style of reasoning that is very important for actually physics and actually many other branches of science, and especially even pure mathematics. So, before I talk into the title of this video, which you might have seen is about me talking about why Johannes Kepler is my favorite astronomer, which he really is, I wanted to first kind of set the stage to justify everything that I'm going to talk about later. And the stage being that, well, we have to go back at a time where people didn't learn this stuff at school, and that being ancient Greece. I'm really bad with specific historical dates, so I'm not even going to try, but I'm going to say some centuries before Christ, you had this fact that many people were beginning to notice patterns of the night sky. Because, for example, if you yourself go outside, you might notice, if you're very patient, that the stars that you see seem to shift around as the hours pass. And especially if you're into photography, you might have taken a long exposure picture that you might have seen these nice arc-wise, you could say, shapes that come from the orbit of these stars that you perceive. We later came to know that these arc-wise trajectories are because the Earth itself rotates around its axis, so we perceive then the sky to kind of rotate around as the night goes on. But people did also notice much more brighter, you could say, stars that had much quicker orbits, you could say, during the night sky. And people were already suspecting that these type of stars would be much closer compared to the ones we see very far away. And this was, of course, later known as planetae, or just planets. This kind of segues nicely into where I wanted to make our story start, and that is Ptolemaic astronomy, or Ptolemy's ideas of astronomy. Because he thought that in order to predict the specific, you could say, trajectory of these planets, then one can use very clever and precise mathematics to do so. More specifically, he used something that was later known as spherical astronomy, where ideas from geometry, which were also being firmly established at the times, could be used to kind of understand when and where a planet might be at some point during the year or at night. And this is an extremely clever endeavor, because this is something that allowed him to catalog very nicely the position of the 5 planets that were known at the time, so Mercury, Venus, Mars, Jupiter, and Saturn, in order then help other astronomers kind of be able to pinpoint when exactly, for example, an eclipse could be seen and things like this. And this is very cool stuff, and he wrote even a whole book on this called the Almagest, which was kind of centuries later used by anyone who basically wanted to learn the art and science of astronomy. So the Almagest was dominant for, as I just said, centuries, but sometime around the Renaissance era, so around the 1400s, there was a Prussian student who became somewhat hesitant on just accepting like things from the Almagest at face value. And that is because the student was noticing that, well, to describe certain peculiarities that you see with the night sky, or of the data basically of the planets, you had to make your model more complicated in order to make it fit these observations. This is mainly, the weird observation was mainly the retrograde motion of certain planets. So the idea that when you're looking at the trajectory, for example, of Mars most notably, instead of having a nice arc-wise thing like this, at certain time of the year, you would notice that the arc looks more like this. It starts nicely, but then it seems to move backwards for a little bit and then continues onwards to its original path. And that is quite weird if you think about it. So what the people did in this more spherical astronomy framework was make the picture more complicated by saying that at each of the planet's own orbit, they have tiny little orbits by themselves which they revolve around. And this held because the fundamental idea of like spherical astronomy or of Ptolemaic astronomy is that the Earth is the center, like the center of things moving around in the sky was the Earth, or roughly around the Earth. And if I'm looking at Mars, and if Mars has a weird trajectory like this, then the way you can explain it is because maybe mostly we're looking at Mars almost kind of head on, but then at certain times of the year, Mars is in a different place around its own little orbit, its own epicycle, and that can explain why it seems to go backwards a little bit until you see it going again at the position which we usually see it throughout a year. But this is something that the student didn't like because he thought that if one wants to make a very powerful model for describing the universe, the cosmos, then it needs to be as mathematically simple and elegant as possible while still explaining a broad range of things that you can actually observe. And this is exactly what the student sought out to do. And this was Nicholas Copernicus. And what Copernicus did was that he thought that, okay, what if instead we change the underlying assumption entirely and shift the point of orbit from the Earth to the Sun? And the reasoning for this wasn't as clear at the time, and it was mostly, I think, based off of aesthetic purposes. But if you're more of a historian on astronomy, do let me know if you know more better. But this simple shift, though, did actually help massively because that picture that things, including the Earth, revolve around the Sun suddenly kind of made sense a little bit of things like retrograde motion, and also made the pictures less messy. You didn't need epicycles anymore. Things kind of nicely fell into place. This was the building block of what kind of later led to the work of Kepler, which I ultimately want to talk about. In between Kepler and Copernicus, there was also Galileo, which also started to kind of take this idea that Copernicus had more seriously and kind of name you that Copernicus' idea wasn't widespread at all during his time, which was like the late 1400s and I think early 1500s. And that is because one of the dominant, you could say, figures of authority at the time was the Vatican Church, the Catholic authority. And they had a lot of authority in governments and finances, so they could really affect people's life in very crucial ways. And this picture of an Earth-centric idea of the cosmos fitted nicely with the biblical scripture, but that of a sun-centric model did not. So people would see this as heresy, and Copernicus was very aware of this and therefore did not kind of openly try to advocate for his ideas. And he instead kind of made the book that he wrote about this, which was on the motion of heavenly spheres. He made it as archaic and inaccessible as possible because he thought that, okay, maybe that way the church wouldn't get to him as quickly. They did eventually start meddling in his life, but it was much later compared to someone like Galileo Galilei, who had the opposite idea, that he thought that, oh, he saw the elegance in Copernicus' idea, especially as he observed the moons of Jupiter with telescopes. He was the first person that thought that instead of just using a telescope for navigation, what if we just point telescopes up in the sky? And he pointed it to Jupiter, and he noticed the thing that many of you maybe have noticed if you look through a telescope at Jupiter, and that is these four very bright little dots that kind of dance around the middle of Jupiter. And these are the largest moons of Jupiter, the now known Galilean moons. And what Galileo noticed is that the placements of these four bright dots tend to change around as you continue to observe Jupiter. And this is very interesting because it means that these dots revolve around Jupiter. They don't stay at the same place. So this kind of made Galileo even more convinced that there is something to, for example, Copernicus' ideas, because perhaps indeed not everything revolves around the Earth. But Galileo was much more loud for it, and that did not do him any favors, unfortunately. But then you skip a couple of years later, and there were astronomers that started to kind of consider the use of this heliocentric model, this sun-centric model, but they mainly especially thought that it is useful for calculations, but this is not kind of the explanation of how the universe functioned. They would still say that the Earth was at the center, and we just use these ideas from Copernicus to kind of make more precise statements. This was, for example, especially the case with the Danish astronomer Tycho Brahe. And Tycho Brahe lived around the late 1500s and early 1600s, and he was known to make some of the most precise astronomical observations at the time. Like, his observations are so precise that people even used it, I think, in the like 90s or 80s or something, like as in like in the 20th century, to kind of predict something about a supernova that he observed, and he and Kepler observed actually. So I'm gonna get to Kepler very soon. So what Tycho Brahe needed was a student who was very careful, very precise, very meticulous, to kind of go through his data and make a nice compendium of all the observations that he did, which was a lot, because Tycho Brahe had a whole kind of like mansion or palace to himself that he could dedicate to observations. The place also had a bit of an occult kind of like lore to it, but that's something for if you're really curious about like astronomy history, look up Tycho Brahe. But in any case, the student that he hired to do this was someone that came from a very humble background who had a strong inkling for doing mathematical calculations. This was Johannes Kepler. And Kepler came in to help Tycho Brahe because he knew of Tycho Brahe's reputation, but also he was very interested in using Brahe's observation to kind of study actually the heliocentric model more carefully. Kepler was convinced already after having read Copernicus' work when he was at university. When he read Copernicus' book, he was very fascinated because he also had a deep, almost spiritual intrinsic need for harmony and kind of elegance. And that is exactly what Copernicus tried doing when organizing this idea of the solar system in a sun-centric way. So he wanted to use just really hard astronomical data to kind of pinpoint and prove the heliocentric model. So he had a lot of tries at this, and his work wasn't smooth sailing at all because there was a lot of kind of bickering between him and Tycho Brahe. But for example, this did lead to many of his most notable contributions. One of the first ones being that he wanted to kind of notice general patterns of planets as they move around the sun, which again, even talking about it as normally as we usually would, you have to keep in mind this was a very daring thing to even ask. So what he did notice is that the motion of planets around the sun, there were patterns in them that were kind of interesting and not trivial at all. And these are that these planets can kind of slow down and line up in very different ways over the span of certain years. And this is called planetary resonance, and it's a very specific astronomical thing. But it showed that this could be explained by kind of considering each sphere of a planetary orbit. This kind of still is tying into the ancient Greek idea of spherical astronomy, that each planet kind of forms a sphere because of their circular orbit around the sun in this case. Each sphere could be determined, at least in their radius, by inserting a platonic solid in between them of different sizes. And platonic solids are things like cubes, polyhedra, octahedra, etc. And this is something that he called the cosmographic mystery, like a mystery of why there is like kind of order in this like structuring of the universe. And he became so deeply convinced that this underlying mathematical pattern was important that he kind of made really good astronomical predictions, because indeed we do see planetary resonance, but he made it for very wrong reasons because he was moved by this almost spiritual, you could say, guide of what the universe ought to look like. Interestingly enough, even though we don't use this cosmographic mystery idea nowadays, what is kind of interesting if you really like your mathematics and have maybe heard a thing or two about topology, is that these platonic solids that he has are things that have the same kind of topological feature known as an Euler characteristic. And I'll leave that for you to kind of play around with yourself. If you know what it is, good. And that kind of goes to show you it's kind of really cool that by looking at these platonic solids as the thing that determines the radius of the spherical orbit, that tells you about these planetary resonances, they have a link with a deep underlying mathematical thing that is not tied at all to physical reality. I think this is something that someone that would really like you could say, a Platonist way of thinking about mathematics, that is, the numbers actually exist and the reality is a representation of a mathematical world, they would love the heck out of this idea. But alas, that work didn't lead to much places afterwards, so Kepler went to focus on the very planet that kind of stumped his mind for the longest of time, and that is Mars. Kepler wanted to understand Mars' orbit to kind of very precisely predict the orbit using the Copernicus model of the solar system in order to prove that you could say model of the solar system, but also to kind of show that that model is not only very good at predicting the orbit of Mars, but it can also tell us why we see, for example, retrograde motion, which I talked about earlier, why we see that apparent backward like trajectory of Mars at a certain point of the year. And he did so in a rather fascinating, elegant, but also time-consuming way. So he basically tried by collecting measurements of Mars using a tool known as a sextant. So it is like this weird kind of tool which you kind of use to align it with angles, like with an object, and you take measurements, say, over every hour or so. And by taking this angle measurement, you can kind of then note these down in a notebook and kind of trace away the trajectory of a planetary orbit in a very meticulous manner. This is a very painstaking amount of work, but because he promised that even Tycho Brahe's death, that he would carry out his work of precision measurements, he continued to doing so, despite their occasional bickering. And it is really good that he did this because this led him to its most brilliant insight, and that is that eventually, after trying different mathematical, you could say, models to describe the orbit, the thing that worked the most wasn't a circle, but it was an ellipse to describe Mars's orbit. And he later actually conjectured that it isn't just the orbit of Mars that is an ellipse around the sun, but it is actually the orbit of all planets around the sun that is actually an ellipse. And this became known as one of Kepler's laws. And it is an extreme, you could say, leap of insight because he didn't make precise measurements of other planets like this. Like he didn't make this meticulous work for Jupiter or for Saturn or for like Venus. Like he did it only for Mars, but how he did come to this conclusion is, I think, the most thrilling bit about reading about Kepler's work. And in essence, he wanted to imagine what would the Earth's orbit look like if you were someone living on Mars. And this is such a bizarre leap of, you could say, thought experiment. I would say even nowadays, because you have to kind of put yourself in that headspace where it's like, oh, you only have data. You don't even have pictures like to kind of go with you to kind of see that, oh, this is roughly what Mars looks like. Now let me imagine sitting in my chair and like looking at the Earth and the sun in the background. No. You only have numbers, and you kind of have to use your imagination to kind of imagine what that orbit looks like precisely. And then kind of even more than that, place yourself in the vantage point of someone in such an orbit. It's bizarre work, but it's amazing because what he found is that, for example, by putting yourself in the perspective of the thing in that orbit, in Mars's orbit, you notice, for example, that the place you're observing it from, which is the Earth, also has an elliptical orbit. It has precisely an elliptical orbit around the sun as well. Not a pronounced elliptical orbit, but still an elliptical orbit. And not just that, but also you can kind of immediately explain the retrograde motion as well. Because when you're on Mars, you don't see the retrograde motion. But what you see is that when the Earth is at its closest approach to the sun, it tends to move a little bit faster than it would usually do. Earth would seem to speed by you a bit more quickly, and this kind of made the picture of retrograde motion make sense immediately. It is, and I'm going to use a picture because it's kind of hard to just do this in your head, which is, again, points for Kepler. It goes like this, if you can imagine it. Like, if you can imagine this is Mars and this is the Earth, and somewhere here is the sun. So the Earth is orbiting around like the sun, and then at some point it moves faster, and you see it picks up and passes like Mars' orbit a little bit. And that exactly is what on Earth is perceived as the retrograde motion of Mars. And it's just beautiful, like geometric reasoning stuff. And this is something that he wrote down in his book, The New Astronomy, or I think in Latin it was Astronomia Nova, but I'm gonna put a picture, don't quote me. And this is where he ultimately presented what we now know as Kepler's laws of planetary motion, including the famous third, you could say, law of planetary motion that relates the distance between a planet and the sun and its orbital period, like why it speeds up when it's closer or slows down when it's further away. So it's really cool stuff, and I think that's why I think Kepler is one of my favorite astronomers because not only did he make very careful observations, like knowing how to use a sextant and making these careful measurements. It's not light work, especially if maybe you've done astronomy. You would imagine it is so painful to do this by these very analog methods. But yet he made really sharp, you could say, predictions about planetary orbits because also of his strong mathematical, you could say, background. So I think the combination of the two made for his work being so good and interesting, which led, of course, to the work of Isaac Newton, who built directly upon Kepler's work like a few years or decades later, almost a century later, I believe. And building, of course, in the sense that Kepler didn't know what was the cause of things revolving around the sun. One can see that planets follow a planetary orbit, but he couldn't make sense of why they did so. Why didn't they just fly away or something else happen? So he believed that the thing that attracted the planets needed to have a type of magnetism that did so, because it was only magnetism that he knew that could have such an attractive, you could say, behavior at the time. So this kind of leads nicely almost a century later into Newton's own work, where Newton began thinking about gravity and also began thinking about, oh, how about pushing gravity on the Earth to its limit? And I think the best picture for this is his nice cannonball thought experiment. Having that in mind, you kind of see how, like, by shooting a cannonball at different speeds, you can get different, like, trajectories of it, like, landing on the Earth. And if you shoot it hard enough, like with the right speed, it would actually just be completely in an elliptical orbit instead of a nice parabola trajectory. And I think that is just the most elegant thing you can think about out there, because it really relates gravity of everyday life, where if something falls, it would form a parabola of a motion. Like even if it just drop it vertically, when it bounces off the ground, if you graph that mathematically, it really looks like a parabolic thing. He mapped that onto the fact that if the velocity is high enough and tangential to the Earth, like if I throw a baseball like really hard, then it can actually go all the way around the Earth and back towards me in a way. So I think that is a really cool like piece of history that I hope people appreciate, because even though the original books are really hard, I agree. Like I have Principia on my shelf, and I actually even like tried to read parts of it. You can read it, but it takes work. But I think it's so elegant to see these ideas that we now take for granted kind of being planted in a way. And it also shows in all of these cases the beauty of geometric reasoning, because geometry can take you at places where your intuition doesn't always lead you to, because you have to trust geometry. Like it's just math in a way. So yeah. I think that reaches the end of this video, because otherwise I can talk on and on about different people that afterwards use geometric reasoning. I think most notably, like the theories of relativity are strongly based off geometric notions, especially general relativity with non-Euclidean geometry. But that is something maybe for another time if you guys like this enough. If not, I also get it. I just wanted to make a video where I ramble a little bit about the history of science, but I hope you really like this. Let me know what you thought about it down below, and let me know if you thought about this topic before already. I hope to see you guys not too far in the future, a bit soon, and bye-bye.